Is it filming?
Hello. You got it? You got it? Look at me.
Hi there, friends of science. My name is Simbarashe Mambiri. Call me Simba.
Hi there, my name is Abdramane, and you can call me Bechir. So we are here today to present to you our fluid mechanics project with Dr. Zhang.
For our project, we're going to explain to you Archimedes' principle, which states that for a body submerged in a fluid, there is an upward force acting on that part of the body that is submerged in that fluid. We call this force the buoyancy force.
So basically, what is the buoyancy force? The buoyancy force is the specific weight of the fluid multiplied by the volume of that displaced fluid. In our case, our fluid is water.
Dude! So, I hope that by the end of this demonstration and explanation, our viewers will be able to appreciate how boats, submarines, and other bodies in water can stay afloat. And to aid us, we're going to add some formulas and more diagrams. So in our concept of the buoyancy force, we'll use a paper boat, which Bechir will make, and submerge it into our fish tank. At the surface of the water, we expect the buoyancy force to be equal to the weight of the boat, which is the mass times gravity. And then we will increase the weight of the boat by adding coins. We expect in each coin increment, our force of buoyancy to increase, whilst the weight is also increasing, until we get to a certain point where, as the boat begins to sink deeper and deeper, the pressure increases, and then eventually the weight of the boat will overcome the buoyancy force and the boat will sink. Buoyancy force minus the weight will always be equal to 0, meaning at the surface of the water, the boat will stay afloat since the pressure is equal to 0. The second formula to remember is that the buoyancy force is equal to the specific weight of the fluid, water, times the volume of the displaced fluid. And the displaced fluid volume is equal to the height of the boat submerged in underwater times the area of the boat.
When we're done with our paper boat, we are going to use our water resistant spray to protect our boat from sinking, since paper absorbs water. We're just going to make sure that we're spraying perfectly all sides of the boat and let it dry.
We calculated the area under the boat to be 0.0106 meters square. Weight is calculated as mass times gravity. The weight of a standard US quarter coin is 0.05562 Newton. The boat is made of a single A4 sheet which weighs 0.04905 Newton. The specific weight of water is 9,810. Okay, for our experiments, we add 5 quarters at each increment. And we measure the H value, which is the depth of the boat submerged in water. We wrote down our value into a table and did the respective calculations.
To calculate our buoyancy force for the boat without any coins, we multiply the displaced volume 5.3 times 10 to the negative 6 cubic meters by the specific weight of water, 9,810 newtons per meter cubed, and our value comes to 0.0519 newtons, which is almost the same as our total weight for the boat. But the discrepancy or the difference in value is attributed to the error in reading off the value of H on the fish tank. As you can see from our experiment results, our values for buoyancy force were calculated by multiplying the specific weight of water by the volume of the displaced water. The displaced water volume is our boat area times the H value. Because of the systematic error in reading our H values from the side of the fish tank, our results for buoyancy force are slightly off from our expected weight values. Expect error in any experiment, but minimize by making an average of several readings.
I hope you have enjoyed our video demonstration of the principle of Archimedes and buoyancy force.
And we hope you now appreciate how boats and submarines and other bodies in water stay afloat through the principle of the buoyancy force. And we want you to know that it has been our pleasure informing you. And on a lighter note, our new design of boat, the unsinkable Zhang, will never sink.